Hi, it's Tim. In this box is the first batch of PCBs for the design of this PIEEE-488 project. Before I show you what I've got in here, let's take a look at how we designed the circuit board and got PCBWay to make it. Let's get started. So later in the show we are going to be making these PCBs, or at least making one of these PCBs. And is it going to work? Stay tuned to find out. Keep watching. In the meantime, how did we get to this stage? Let's find out. Now I want to thank PCBWay for sponsoring this video. Even though I did pay for these boards myself, we are going to see throughout this video how they were designed, how they were manufactured, and PCBWay is instrumental in producing these boards. So thank you once again. I want to thank them, and let's get on with it. So here we have the GPIO connector that goes to the Raspberry Pi, and our three ICs, the 75160, the 75161, and the 23017. Now they're connected up basically exactly as we had them on the breadboard. There are, however, a few slight differences. So this is the IEEE Centronics connector, but I've also added a 2x12 pin header, which lets us plug in either test probes or a ribbon cable of some sort, so that we, instead of going through the Centronics, we could go directly to a edge connector by building up a little ribbon cable from that. It gives an alternative connection route. And then the two buzzers, buzz1 and buzz2, I've added a little 2-pin jumper for each, which basically just lets us turn the buzzer off if we don't want to have it. And I've added an extra switch on each side. So we've got the B side and the A side, 1, 2, 3 and 4. So this is up, down, select and eject for both drive 0 and drive 1. I've added switch 9, which goes to GPB7, and that is basically going to be a reset. Now over here, this is the 4-pin connector. That is the I2C connector for the OLED. It looks kind of backwards because it's oriented the other way around on the schematic. I could turn it round and have it coming down, I suppose, rather than going up. But pins 1 and 2 are variously either ground or VCC, and that depends entirely on which OLED display panel you happen to get. It could be either way round. And so I have to admit, I sort of half nicked this off the Pi 1541. But this is just a series of solder bridge jumpers that lets us select between, if we go through here, it either goes this way to ground or it goes this way to VCC, and the same with this one, it either goes that way to ground or that way to VCC. So we have one of these is going to go to ground and the other one is going to go to VCC. I've also got it that VCC allows us to switch between 3.3 volts and 5 volts. Most of the time it should be okay to use 3.3 volts. Anyway, it's there as an option. So back on here, we've got the switches and the LEDs. Now on our breadboard, we had 4 LEDs. We had D1 and D2, which were the activity lights. And we also had D3 and D4, which were A, the error light, and B, the power light. And what I've done is I've combined these into a single bi-coloured LED. So this is a single LED that changes between red and green, depending on which side the voltage is applied to. And in order to have this switch between red and green, rather than say red and orange or red and yellow, what I've done here is basically a simple NOT gate that's comprised of one transistor and one resistor. And basically how this works, we're using A5 as the error channel signal, and when this is low, which is the normal state, then this transistor is going to be off, and that means that there's no current that flows between the collector and the base, the collector and the emitter, and therefore this LED number 2 is going to be on, so that's going to be powered through this resistor down to ground. When this signal is high, then the transistor turns on and this will short out, and so current will flow from the collector to the emitter, and this light will be off, and so the current will flow from here through. This will be at high, and that is going to go to ground through here, so LED 1 will turn on. So this basically forms a NOT gate. Then the other additions that we didn't have on the breadboard are these 3 filter capacitors. They're just 100 nanofarad that go between the VCC and VSS pins on the chips. So I've laid this out on a PCB that is slightly bigger than a Pi hat. Let's bring this up. So we can see these are the 4 screw holes that would be a regular Pi hat. So a regular Pi hat is going to be basically that size. This is the GPIB header, and this is the IEEE connector. This is the OLED. This is the 160. This is the 161. This is the 23017. We have our 2 buzzers, our 3 LEDs, and the switches are arranged down each side. Reset switch at the back. So I spent basically a couple of days laying that out, and then we can have a look at this in 3D view. There we go. So these are our buzzers. There are 3 LEDs. ICs, the resistors. 4 of those are the drivers for the LEDs, and the other one is the driver for the transistor, which is our NOT gate. This is our pin header for the OLED panel, which is going to sit down over these resistors in this chip. Switches down the side. That's our header for the IEEE, and this is our IEEE connector. Now, I could only find one CAD model for that, and it's actually a male, although this is actually a socket, and on the manufacturer's website this actually is listed as being the socket, but it's the wrong connector. Somehow they've managed to get the same 3D model for both the male and female connectors, which is a shame. And then underneath we've got the connector for the Raspberry Pi, and these are the 3 little solder pads that we need to set to configure the OLED. Buttons are down each side. Now I've got these set up so that they are the same looking at them like that. So up, down, select, eject. Turn it round, up, down, select, eject. You could also have them up, up, down, down, select, select, eject, eject. I don't think that's the right way around of doing it, but it's possible. Anyway, tell me in the comments if you think that that would be a preferred way of doing it. And this is going to be the reset switch. So really all that remains is to produce the Gerber files for this and order the PCB. So let's do that. Before we can produce Gerber files, we need to go through and do an error check on the circuit board. So we need to run the DRC control. DRC stands for Design Rules Checker. So let's run that. Okay, it tells us we've got some issues. So let's have a look at these issues and see if we can fix them. Silkscreen overlap. Line on back silkscreen, PCB text, VCC, pin 1 ground. Okay, that's here. And what we've got is this little, it's this little indicator that flags pin 1. So what I'm going to have to do is move that out here a bit further. And then I'm going to have to move this a little bit in order to not have that overlapping, and then we're going to have to move this a little bit. There we go, and move this a little bit. And then move this a little bit because it's not quite centered now. Okay. And this one is actually the same error because you can see two arrows there. So that should have done both of those. Now, error silkscreen overlap. Okay, I think this is actually the same error as well. So if we run the DRC again, hopefully it will show it's okay. Error 0, warning 0. Yep, that's okay. Right, so we've fixed that, and let's now go back to our 3D viewer and just have a little look on the bottom and see. Oh yeah, okay, so this is where it was causing a problem. Hopefully that's clear as to what it is. So this is pin 1 and you connect that to VCC that way, or you connect to ground that way. And I've got them so that they're both the same way around, so it's down for ground and up for VCC, and VCC of course is up here, and then you select either that way for 3.3 or that way for 5 volts. Right, so now let us create our Gerber files. So file plot. Front copper, back copper, front silkscreen, back silkscreen, front mask, back mask, and edge cuts. Plot. Now generate drill files. The defaults, I believe, are okay. Recommend, yeah. And it says done. Okay. So close that. Save that, exit out of that. Now what we're going to do is we're going to look at Gerber viewer, and this is going to preview our Gerber files. So open drill file, and we're in the Gerber's folder. And drill files are .drl. We've got two drill files. The PTH is plated through holes, and the NPTH is the not plated through holes. So I hope that makes sense. This is going to be basically the 4 corner holes for mounting the board onto the Raspberry Pi. And now we can open the, for some reason, the second time you do it, it goes right the way back to the root. So Gerber's plated through holes. So these are all the pin connections, the vias, the headers for the ICs, the headers for the connectors, and they're plated through holes, the switches and so on. So now we look at the edge cuts. This is basically the board outline, and if we had any slots that we wanted to cut inside the board. So for example, on some hats you've got a slot for the ribbon cable for the camera and so on. That would be included on here, but we've only got basically the outline, which is a rounded rectangle. This corner is a tighter corner than these other corners, simply because the IEEE connector goes up to here and it would overlap the corner with a wider radius. So far that looks okay. Now we're going to layer the other plot files on top so that we can see that everything lines up. So the next thing that we're going to look at is the front silkscreen. There we go. And that looks like it's all in place. Then we're going to add the front copper, I think comes next, in shocking pink, and we need to check that that lines up. Now over in this corner we've got the various layers that we've opened up. I can slide that out so we can turn on and off the copper and just see if there are any sort of strange movings and disconnects, and that does seem to be okay. And the final layer is solder mask. Okay, so that seems okay. So we'll turn the front layers off and just quickly do the same for the back. Now remember, we're looking down on the board, so it's going to be reversed. So in terms of the writing on the silk screen. So that looks okay. We've got the solder pads and we've got the connector for that. So now we'll add the back mask, toggle it on and off, see that there's nowhere that is obviously misplaced. And the final one is back copper. And that looks okay. We don't need to save anything there. So all we do is simply we go into our Gerber's folder and simply zip up the files, and we're going to call it gerber.zip. So there we are, and we can just have a look and we can see that that is literally about 300k. So now we can go to PCBWay. We have to be aware that it's Chinese New Year, and so I suspect things are going to be slower today than they would normally be. But that is the way of things. So, PCB instant quote. And what we've got the size of this board is, I happen to know this, it's 80mm by 70mm. And we're going to want 10 because it's as cheap as anything to have 10. 2 layers. I'm going to go for green. I never buy green, so let's buy green. Silkscreen is white. All that is normal stuff. Pricing and build time $5. We are going to the UK. So DHL $29. FedEx $19. Well, 4 to 6 business days, 2 days longer, but $10 cheaper. Are we in a rush? No, we're not. So, what we do now is we upload the Gerber file. And now we've done that, submit. And that will go off and the Gerbers will be checked, and we'll come back in a little bit and it will be ready for us to review and pay some money. So the moment of truth. Yes, I have gone for green. Okay, and this is the board. This is obviously take 1. Right, so I had a sleep on it and I ended up relaying out the board. Now I've made it a little bit wider, so it's now 80mm by 82. The extra 2mm just gives this connector a little bit of clearance from the holes. Doesn't quite make it a nice round number, but never mind. And the reason that I did that is that now these LEDs are more evenly spaced across the width of the board. So this is now in the middle, this is the center line, and the center line goes up through the OLED. So the OLED is now central, the connector is central, this connector is central, which is just really aesthetics. And this now overhangs this side of the board by the same amount that this overhangs this side of the board, and so it's even. And so let's have a quick look at the 3D view. That looks pretty good. So these are the bridge connections for determining what kind of OLED panel we've got. Shall we see if stuff actually fits on it? Right, I've got the board and I've got the bits. So we have jumpers, we have sockets, chips, and circuit boards, resistors, diodes, capacitors. So we'll start with the resistors in the middle. We have 4 330 ohm resistors, 4, and one 1K resistor. There we go, it goes in. So the momentous first blob of solder. There we go, look at that. So I'll just put all the other ones in. So these of course are 4 resistors for the LEDs and 1 for the transistor. There we go, 4 resistors. We'll probably put the capacitors in next. These are just 100 nanofarad decoupling ceramics. Transistor can go in. Right, I'll put the sockets in. 2 20 pins and a 28. So those are the 20 pins. This is the 28 pin. Now obviously this is the narrow form factor, not the sort of 28 pin socket that you would expect for an EEPROM. Right, LEDs. This is the bi-colour LED. It's important to get these the right way around. The flat sides are all facing that way. So what I can do with this is cut it into 2 and use it for these pins here. Right, I want to solder that in before too long, but I haven't got any double headers for this, so what I'm going to do, pick a colour, let's have blue. What I'm going to do is make 2 single headers. That's 2. Like that, and then I'm going to plug this into the top like that, and that is going to align them up. So as in the normal way, we just solder the edges, check that they are straight, which they are not. Okay, but there we've got our double header, so now we just need to solder that in. There we go, and the purpose of this header is so that we can put on either test leads or we can connect a ribbon cable. We can put this on now. I'm going to sort of support it there like that. Now I'm not going to cut these legs down because they will be useful again as test leads. Now switches. If I buy more, I'm going to buy them with a longer pushy bit. These are quite short. But they simply push in. You don't always know what you need until you get them and you find that they're the wrong one. Two outside pins are just for stability. Now I'll put some screws and nuts and bolts in there at some point to mechanically secure it. And that just leaves the two buzzers. So plus is marked. There we go. And finally, let's put my anti-static on. And one of those, which is this one, and the 161 which is this one. And there we are. One last thing, we have the OLED screen to put on. It's designed so that it's in the middle of the board, not in the middle between these two chips, because of course those two chips are not quite centered. Going to the thing. So what we have to check on this is which of these first two pins is ground, and then set the links accordingly. And pin 1, the first pin, is ground. You can see that. So on the back, pin 1 is ground. So we want to set that, and then pin 2 is VCC. And the power supply is going to be 3.3 volts. So that's our jumpers set. There we are, the PIEEE-488, first one, very first prototype actual board. Stay tuned and we'll find out if it works. So I've put standoffs on it. They're brass at the moment, but I would probably change those to nylon. I mean, electrically they're fine, but poor man's turntable. All that remains, and I'm quite pleased that everything lines up. All the standoffs line up, plugs in nicely, and I guess I have to finish the software and make it actually work. I need longer M2.5 bolts to hold that down. These are M2.5, but they're not really long enough to screw in. So I'll move it over to the development board and we can plug it in and try it. See if it actually goes. So, admission time. I made two basic problems on this circuit board. First one was that the two-colour LED, I gave it completely the wrong footprint. The one that I picked was anode, anode, cathode, whereas what it should have been was anode, cathode, anode. So I've had to take the LED out and stick it on some wires. The second problem, and this is probably even more significant, is that I wired up the IEEE connector backwards. So it would work, but you'd have to put the connector, instead of being that way up, it would have to be that way up underneath the board. And that would have been fine, apart from the fact that this IEEE cable is thick as anything, and it doesn't bend very easily, and it's basically one directional in that it goes that way, or from, if it's plugged in correctly, it goes that way, and it ain't going to change direction very easily without me completely rearranging my desktop. So I used the IEEE connector off the breadboard version and just extended the wires to this little header that fortunately I put in. So all these little pluggy in wires, except for this one which is in the wrong, fallen off, these go to this little logic analyzer, which goes to the logic analyzer on my PC. And this is the setup that we have, and let's just zoom out a bit. So we've got the Pi down there, screen for the Pi, screen for the PET, PET over there, remains of the breadboard in the background, and there is our little circuit board. So the $6 million question is going to be, does it work? Well, the answer to that is yes and no. Sort of. The hardware is working, it works fine. The signals do the appropriate signally thing. The problem at the moment really is to do with the software. Let's just switch it on and you can see what happens. It starts up with a little diagnostic sequence. There we go, it just flashes the LEDs and lights up the OLED. What happens when we actually try to access the disk or access the drive is this. Right, standard directory command. And you can see it gives us a device not present error. So the problem is, I'll show you this on the logic analyzer screen. ATN gets triggered and we respond by setting NDAC low. Now the problem is that we're not setting that fast enough, and so it times out. We have just 120 microseconds to set that. So let me show you. Here we go. So as soon as the event is triggered, First thing that we do is set NDAC low, and then we do other stuff. But that first thing is taking longer than the time that we have, which may mean that Python is not going to be suitable to do this interface in. So I'm going to have to think about either some way of making it faster, compiling it, or some such, or try using a different library, maybe would be faster, or possibly it's going to have to be written in C. Maybe just the library needs to be written in C, or at least the port handler needs to be written in C, but it needs to be thought about. And so that's what I'm going to do next, and in the next update hopefully I will have something more positive to show you. Anyhow, this is just a project that I'm tinkering with off and on, so if you're interested in more frequent updates or more updates with this, then please let me know in the comments. But otherwise I will update you as and when I think I have something to update you with. It's, you know, it's my Christmas tinkery project, and we're now into February and I'm still tinkering, but it's fitting in with everything else. You know, I have to figure out how to program this thing. I have to figure out how to program the Pi. I have no idea about programming the Pi in C. I have no idea about writing the device drivers for it. This is all stuff that I'm going to have to learn or teach myself. And so this is not going to be a quick project. This is going to take a while. But, you know, I'm in no hurry. It doesn't have to be finished next week. One day it will be done. Then I'll have to decide what to do with it. Your suggestions there are welcome. Anyhow, tell me if you like this sort of content. Let me know in the comments, and like and subscribe to the channel if you want to see more. And I will see you another time. See ya. Bye.